Welcome everyone to my talk. So I'm going to be talking about basic electronic simulations to model solar cells. So essentially going from the equations to the most important aspect of a solar cell, which is the current voltage curve, and also what kind of things we can learn about the device physics through this modeling. Yeah, and the second part of my talk will also be a little bit about the machine learning work that's been going on in the group of Professor Thomas Ketschartz in Duisburg. So specifically the use of a neural network to infer material parameters. Okay, so we start from the very basic point where you measure the current voltage curve of your solar cell. So here you have a solar cell and you have a simulator that simulates the spectrum of the sun. And it's connected to a source measure unit here. And you get your current voltage curve, right? And your typical current voltage curve looks like this. So just as an example, I've taken a perovskite solar cell here. So that's a perovskite absorber, which extracts electrons up there and holes down there. Yeah. And the key features of the JV curve are as follows. So you have a short circuit current density, which is the current measured at 0 volts. And you have an open circuit voltage, which is the voltage measured when no current is flowing. And you have a maximum power point over here, which, as the name suggests, is the point where the solar cell generates maximum power across a load. Yeah. And the efficiency is given by this formula. So you have the JC times VOC times fill factor divided by the input power. And the fill factor is given by the current multiplied by the voltage at the maximum power point divided by the short circuit current times the open circuit voltage. So essentially the squareness of your current voltage curve. And the modeling basically starts from a semi-classical situation. So here we are already assuming we have a crystal with a well-defined band gap. And so you have your conduction and valence bands, and you have your distributions of electrons and holes that obey the Fermi-Dirac statistics. So here you have the band diagram at short circuit. And you can see that you have the electron and hole Fermi levels that are separated. This means that it is away from an equilibrium situation. And here you have the corresponding situation where there's no current flow at open circuit, and which shows that the Fermi levels are essentially flat in the absorber. And here you have the band diagram at maximum power point. So I just show you how it looks when you shine a photon on the solar cell. So this photon is absorbed by the perovskite and you generate electron hole pairs. So electrons in the conduction band and holes in the valence band. And then these are driven by different gradients, hopefully to the correct contact. So you want your electrons, for example, in this situation to go down this gradient, down this electric field, and you want the holes to go the other way and get collected at the opposite contact to generate the current flow. Okay, so now how do we model this? We start from a very basic situation. As I said, this is semi-classical macroscopic modeling, and we stick to one dimension. So then you have the simple situation of the continuity equation here. And it's essentially just balancing the different fluxes in the solar cell. So this equation here is the continuity equation, and it's telling you that the change in the electron concentration, so that's per unit volume per second, is equal to the generation, which is the number of photons that are shining on the sample and generating electron hole pairs. So that's the generation rate minus the recombination rate. So the electrons and holes are recombining at a certain rate as well. And this term here is basically the gradient of the current densities here as a function of position. And these are transport fluxes basically. And this transport flux comes from two things. So the diffusion of charge carriers under a electrical gradient of electrical potential, or you can also have a gradient of chemical potential that generates a flux of carriers along the x-axis. Okay, and then when we measure the JV curve, of course, we want to know the steady state behavior, which means there is no change in the concentrations versus time. So this left side just becomes 0. And then we can calculate the current density J as follows, as just the integral over the difference between the recombination and generation in the solar cell as a function of position. Okay, so the next step is essentially connecting the recombination term to the carrier densities in the solar cell. So we can be more specific with that and say the recombination is proportional to exponential the gradient of the Fermi level. So this is the difference between the electron Fermi level and the whole Fermi level, right? So this is a fundamental equation here that goes in, and then you end up with this equation here. So you have a recombination term that depends exponentially on the Fermi level splitting, which is basically the number of electrons and holes in the solar cell. And then here you have a generation term. Again, this would depend on your optical model. So it depends on the different layers that are in the solar cell and the absorption capabilities of your solar cell. And then there is a small assumption here that happens, which we will talk more about later. So here you say that the quasi-Fermi level splitting in the absorber is equal to the voltage that you're applying. So the voltage is basically the difference in Fermi levels of electrons and holes at the edges of the solar cell where you have your metal contacts. Yeah. So let's just assume for now that this assumption is true. We will talk more about that later. And then what you end up with is basically the fundamental diode equation, which many of us know. So you have the current equals a prefactor J0 times exponential QV by KT minus 1. And that's your recombination current versus voltage. And then you have your short circuit current, which is all this generation term here. And of course, in reality, it's slightly different. So the previous equation that I showed here is an idealized version of the diode equation. In the case of other recombination mechanisms, like for example, recombination through defects, dominating the response, then you have to account for that using an additional factor, and this is called the ideality factor of recombination. So the ideality factor is 1 when you just have radiative recombination, and 2 when you have, or between 1 and 2 when you have defects in the solar cell that are also dominating the recombination. Okay, now that we know about the continuity equation, let's just switch to the dark situation here. So we're not shining any photons, which means the generation term is 0. And then you have the continuity equation as follows. And then your total current is just the integral of the recombination rate through the entire device, right? And then you again end up with this diode recombination term here that I just showed. And in case of a PN junction, of course, here you have the P layer where the where the whole Fermi level is fixed, and you are applying a voltage and just changing the minority carrier density in the device. Yeah? And this would be a kind of simple representation of the recombination current in the dark. Yeah. So in reality, this would also depend on the diffusion length of the minority carriers, in this case, the electrons in the p-type layer, and also the surface recombination at the boundary. Yeah. So again, a similar situation, instead of a PN junction, if you had a PIN junction, so an intrinsic absorber layer, again, you have the same equation, but your ideality factor will change depending on the division of electrons and holes. Okay, now from the dark situation, we go to short circuit under illumination, and we stick to an idealized condition, which means there is no recombination at short circuit. Since the recombination term here you see depends on the voltage, so when V is 0, there should be no recombination. So then again, the continuity equation is simplified. So it just depends on this, on the generation of carriers. Yeah, so essentially how the carriers are absorbed. So for example, you could use the Beer-Lambert law to calculate your generation profile of carriers in the absorber. And the integral of that gives you your short circuit current, the JSC. And again, moving from a doped sample to a kind of PIN situation, it's here you would have a voltage dependent collection again. I'd just like to note that again, since this is an idealized case, we just use this equation, but in reality, there is a collection probability term that has to go in here as well. That again depends on the diffusion length and the surface recombination terms. Yeah, and in case of a PIN junction, you also have a drift length that would come into this collection probability. So the drift length is the product of the mobility times the recombination lifetime times the electric field in the PIN solar cell. Okay, and finally, we come to the open circuit under illumination situation. So essentially here, the internal voltage is equal to the external voltage, and the Fermi levels are flat and there's no current flowing, which means the generation equals recombination there. And so just equating the two terms of generation and recombination, you get to the dependence of the open circuit voltage on the short circuit current. Yeah. And again, it's a similar situation for the PIN solar cell. Okay, and so combining all these insights, we can look at the continuity equation in a general situation where you are away from both the short circuit and the open circuit situations. So this is an interesting situation where you have the generation term, the recombination term, and the flux terms. Yeah. So here I've just drawn a band diagram. Yeah. So you have an applied external voltage. That is the difference of the electron and hole Fermi levels at the edges of the solar cell, as I mentioned. That's your Q times V. And then you have a quasi-Fermi level splitting in the device. And this quasi-Fermi level splitting is a function of position. It need not necessarily be flat. And you can see that it is changing quite a bit through the solar cell. So for example, here you can see that the quasi-Fermi level splitting is much bigger than the applied external voltage. Yeah, and this quasi-Fermi level splitting is very important to drive the current in the solar cell. So for example, the electron current density in the solar cell is given by this equation. So it depends on the conductivity of the electrons and the gradient of the electron Fermi level in the device. So a larger gradient implies a larger electron current is flowing at that point. So what we can understand from this is that in order to have a current flowing, you need this quasi-Fermi level splitting generally bigger than this external voltage, yeah, which is quite different from our previous assumption where we said this delta EF equals to the external voltage. So the consequences of this will be shown in a bit. But before that, I just want to talk about the basic recombination mechanisms that are involved in this modeling. So we have three different mechanisms. We have the Auger recombination, the Shockley-Reed-Hall recombination through defects, and you have radiative recombination. So the first recombination mechanism is the Auger recombination, which is relevant for silicon solar cells, for example, with the high doping densities. So here what happens is that you have some electrons in the conduction band and holes in the valence band, and the electrons recombine with the holes. And this energy, this recombination energy, is transferred to a third carrier that is excited, and that eventually loses its energy through the emission of phonons or lattice vibrations. So this is a three-carrier process, which is a model typically using this equation. And in general, the recombination rate can also be modeled and is frequently modeled with this equation here. So the recombination is the excess carrier density divided by a lifetime tau. Yeah, and this tau again is not constant. So it can also be dependent on the carrier density. And okay, next we move to the radiative recombination mechanism. So this is very important for the solar cell. So for a good solar cell, you want to maximize the amount of radiative recombination, and you want to minimize other non-radiative recombination mechanisms. So in this case, you have an electron in the conduction band that recombines with a hole in the valence band, and you have the emission of a photon whose energy corresponds to this energy difference. And the recombination is the radiative recombination is two-carrier process. So you have the product of electrons and holes here with a prefactor K. And the final recombination mechanism is something that limits the performance of the solar cells a lot and leads to the loss of the open circuit voltage. This is Shockley-Reed-Hall recombination through defects that have energy levels in between the band gap. So essentially, the electrons from the conduction band relax down to the valence band non-radiatively, that is by the emission of phonons via this intermediate defect state. Yeah? And the equation for modeling this recombination is a bit more complicated. You see that here. So essentially, this equation comes from considering both the capture and emission of electrons and holes from these defects, right? And I just explained these terms here a little bit. So this you have again this NP, so the product of the electrons and holes minus the equilibrium concentration. And then here you have a tau P and a tau N, and these are given by these formulae here. So they're the inverse products of the capture coefficients of the electrons and holes times the defect density. Yeah. So if these capture coefficients are high, it means there's more probability of an electron or hole getting trapped in the trap. And of course, if you have more defect densities, that means there's higher chance of more carriers being trapped. So essentially the lifetime, which is how long the carrier exists before recombining in the band, is given by the inverse product of these two. There's additional terms here, N1 and P1, and those are basically terms where, so N1 corresponds to the electron concentration when the electron Fermi level is coinciding with the trap energy level, as you can see here, and vice versa for the holes. Yeah, so these N1 and P1 terms become quite relevant when you have shallow traps that are close to either the conduction or the valence bands. But in the case of deep defects, they are frequently neglected and the whole equation simplifies. Okay, so that's a basic summary of the recombination mechanisms. And so combining all this information, you end up with, again, this diode equation for the recombination as shown here. And then you have the generation current here that is basically overlapped on top of it. Yeah, so this is a key facet of this superposition principle that's mentioned here, where you can essentially model the behavior of the solar cell under illumination as its dark recombination current superimposed on the generation current, which is your short circuit current, right? And we can also add additional non-idealities in the model. So this is through series resistance. So this could be something due to your metal contacts, your ITO, or your wiring, for example. Yeah, it's just a simple external series resistance. And you can also have a non-ideality in the form of a shunt resistance. Yeah, so this is a parallel resistance to the solar cell that's shown here. And this would induce additional recombination. Yeah, so the solar cell essentially is modeled in the form of a diode here, which is this equation, and the current generation element that is your JSC, your short circuit current. And finally, what you end up with are these different JV curves. So this comes going from the continuity equation to the diode equation to the superposition principle. Then you finally end up with your current voltage curves here. Okay, I'll just talk a little bit about the effect of these resistive elements. And this will be relevant for the photo shunt that I will talk about next also. So here you see the effect of a external series resistance. So essentially it creates an increased potential drop through the device. And this leads mainly to a loss of the fill factor in the solar cell. So you see that here. And in the case of a reducing shunt resistance, it just means you're increasing a parallel path of recombination. And then the solar cell starts behaving less like a diode and more like a ohmic resistor, as you can see over here. So both these resistances are not good for the solar cell and decrease the performance. Okay, now we move to an interesting topic, which is the limitation to the superposition principle. And to explain that, I just showed this graph over here. So the red spheres here are a typical current voltage curve under illumination. Yeah. And then you can take the dark current voltage curve and then superimpose the short circuit current on top of it. Yeah. And so then you get a current voltage curve from the dark JV curve. Yeah. So this is essentially testing the superposition principle. And if the superposition principle was correct in theory, then the red and the blue should be overlapping, which they do not, right? So there's a fundamental difference here. Yeah. And to further understand this, you can also measure the short circuit current of the solar cell at a given light intensity, and then measure the corresponding VOC at the same light intensity and plot that JV curve for different light intensities. So this would essentially be an open circuit version of the current voltage curve. And essentially that means it is free of any resistive effects, series resistive effects. And you can see that pretty much aligns with this, though it's different from the red curve. Yeah. So another way to understand this would be to compare the recombination currents in the dark and under illumination. So according to the superposition principle, they're both the same. But if you just look at this curve here, you can see that they're very different. So here you have the dark recombination current. And then here is the recombination current under illumination. So you essentially take this red JV curve and subtract the JSC. Yeah. And you can see that under illumination, there is a much bigger recombination current compared to the dark situation. And this is called the photoshunt effect under illumination. Yeah. And this essentially arises from the fact that the internal voltage and the external voltage are not the same under illumination. Yeah. So the internal voltage would be the quasi-Fermi level splitting in the solar cell that is needed to drive the photocurrent. And your V is your external voltage, of course. So for example, at short circuit under illumination, you still have a large number of electrons and holes in the solar cell under illumination. And this means the large quasi-Fermi level splitting, delta EF, which also means that you have more recombination, since recombination is proportional to exponential of the quasi-Fermi level splitting. Yeah. So this big difference in the internal voltage and the external voltage is the reason why there is more recombination, which means a lot of the characterization efforts also have to be focused on modeling recombination, not just close to open circuit, but also across the entire current voltage curve in order to account for all the losses that are happening in the solar cell. Yeah. And this photoshunt is also kind of a universal feature of solar cells. So this was already noted in 1994 by this really nice paper by Robinson et al. So here they do the same thing. So they compare this dark recombination current and also the recombination current under illumination. And as you can see with higher illumination, there's more Fermi level splitting and hence more recombination as a function of voltage. And you can also see this across technologies. You see it also for the perovskite solar cells. You see it here for the case of organic solar cells as well. So there's an excess recombination current, which significantly affects the performance. And this recombination current is also tied to other layers that are extracting charge. So for example, in the perovskite, you have electron and hole transport layers, which have relatively low mobilities, and they're essentially acting like an additional series resistance. And that also affects the amount of recombination in the bulk absorber. Yeah, so all the layers in the solar cell are kind of coupled in the case of the recombination. Okay, so now I switch to the last part of my talk. So so far I've shown the different equations that are needed to model the solar cell and to produce a current voltage curve. And this is quite interesting to put in different parameters and simulate current voltage curves. However, a lot of times, what is more useful is the reverse problem, where you have a current voltage curve that you have measured experimentally, and you want to get out the material parameters from that current voltage curve. So for example, these parameters would be critical to know what is limiting your device or which layer is limiting your device, right? So the examples of these parameters are this absorption coefficient alpha, the charge carrier mobility, the charge carrier lifetime, the transport layer resistances. There's many different parameters that we ideally want to know, because then we can make an appropriate modification of our fabrication process, for example, to overcome this limit. Yeah. So the question is, what would be a good way to do that, to extract material parameters out of your characterization data? And the traditional way of doing that is as follows. So you put in some material parameters into your simulator, and you use the equations that I showed earlier. And that simulates the current voltage curve, and you compare the current voltage curve to your experimental current voltage curve, and you obtain some best fit parameters. Yeah. And in certain cases, this works. So in very simple cases, but a lot of times there are too many parameters to get a good fit. And there's also a lot of correlations between the parameters that are not, whose information is not provided just from fitting. Yeah. So in such a scenario, what is more useful is not just a best fit, but also a likelihood or a probability of the parameters existing in a certain range. And in order to do that, you need to switch to something a bit more complex, which would be a neural network surrogate workflow as shown here. So again, here you need to build a neural network that is trained with a lot of simulation data from these numerical solvers like SetFOS and SCAPS and stuff. So you train a neural network with plenty of simulations, and then you show some experimental data to this neural network. Yeah, and essentially the neural network acts as a interpolator, so it can also generate JV curves between your material parameters in order to compare it with the experimental data. And from there, you need an algorithm that that analyzes this and makes a best fit, and also generates this probability density landscape as shown here of the parameter existing in a certain range. And the advantage of this neural network workflow is that it's much faster than a typical typical simulator for the JV curve. So you can see it can generate more than 12,000 JVs in approximately a second. So this is a good way to speed up your workflow. And so here is an example of the test of this workflow on a synthetic data set. So here you have JV curves, 4 different JV curves at different light intensities of an organic solar cell. And the idea is we want to estimate several of these parameters shown here. And to do that, the algorithm used is this CMAES algorithm in conjunction with this neural network that I just described. And here you can see how this algorithm rapidly scans the parameter space in order to hone in at the right values of these different parameters. So the simulated parameters are the chosen parameters for simulation are shown with these stars here. So I just play this video. Hopefully you can see it. So you can see that the algorithm allows, instead of sampling the entire grid, it allows you to hone in on the correct value by clever selection of the parameter space. Okay, and here I just show how the information that is provided helps also in identifying the correct probability distribution of the parameters. So here only one JV curve is fed into the neural network. And these 2 red lines are where the chosen parameters are. And you can see that the probability distribution is pretty wide. And then you feed in the next JV curve, and then the probability distribution is more focused. And as you keep going along that line, you see that you reach you reach the right parameter values that you want in this probability distribution. Okay, so that was a summary of the work that's been going on in regarding the neural network, and also I made a quick description of the different equations that are used to go from the equations to the current voltage curve, and to do some of the electronic simulations that we are doing to characterize the solar cells. So I'd like to acknowledge Professor Thomas Kirchhartz and Unchi Kim for the slides, and also the Solar Tap for funding.